How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for the gas laws. All right, so we got pressure, volume, temperature relationships. Let's take a look. So number one, we have a 5.0 mole sample of a gas at 1 atmosphere, and it's expanded at a constant temperature from 10 liters to 15 liters. What is the final pressure in atmospheres? So I always start with what they call the combined gas law. So I get P1 V1 over T1 has to equal P2 V2 over T2. And all that's saying is if you have a sample of gas at some initial pressure, volume, temperature, PV over T has to equal whatever the new conditions are for that same sample of gas. Now, the reason I start with this is now I can just cancel out anything that is held constant. It says that the temperature is held constant. So I know that T1 equals T2. So that means I can just kind of cancel them out on both sides since they're the same thing. And I'm left with this equation. P1 V1 equals P2 V2. So now I go, hey, what is it asking for? Well, it's asking for the final pressure. So I'm trying to get P2. So I divide each side by V2. So I get P2 by itself. Here, the V2 cancels out. Boom. I now have my equation set up to solve for P2. So let me just plug and chug. My initial pressure, they said, was 1 atmosphere, so 1.0 atm, times my initial volume. Well, it says it goes from 10 to 15, so my initial volume is 10 liters, divided by my new volume, V2, 15 liters. And when I do that math, the liters cancel out, and I end up with a pressure of 0.67 atmospheres. There you go. All right, number two, if a 50.75 grams of a gas occupies 10 liters at STP, or standard temperature and pressure, how many liters will 129.3 grams of the gas occupy at STP? So we know that as we increase the number of moles of that gas, then we're also going to increase the volume. So basically, we have a proportion here. We know that for every 50.75 grams, we occupy 10.0 liters at STP. Let's say, all right, well, if we had 129.3 grams of that same gas, what would the liters be? So you can set up this proportion and you can cross multiply and divide. And when you do that, you end up with, where did I write it down? 25.5 liters. So that's all. Cross multiply and divide. All right, number three, a 1.5 mole sample of a gas is contained in a 15-liter rigid cylinder. So the key here is this rigid cylinder is telling you that the volume doesn't change. You know that volume 1 equals volume 2. That didn't change. It's a rigid cylinder. All right, so the temperature is increased from 100 Celsius to 150 Celsius. What is the ratio of final pressure to initial pressure? All right, so again, I start with P1 V1 over T1 has to equal P2 V2 over T2. And they're saying that, hey, V1 equals V2 because it's a rigid cylinder, so they cancel each other out. Now, the temperature here, we got to convert it to Kelvin. So 100 Celsius is 373 Kelvin. This would convert to, sometimes simple math just trips me up, 423 Kelvin. And they want to know what is P2 divided by P1. So I got to rearrange this a little bit. I got to divide each side by P1. And then I got to multiply each side by T2. So here the P1s cancel out. Yeah, the T2s cancel out over here. So P2 over P1 has to equal T2 over T1. So now my T2, my new temperature, is at 423 Kelvin. Divided by my original temperature, 373 Kelvin. And the ratio that I get when I do that is 1.13 times. So what is the ratio? It's 1.13 times greater. All right, number four, a sample of gas originally at 25 C and 1 atmosphere pressure is in a 2.5 liter container and has its pressure dropped to 0.85 atmospheres, and the temperature is also decreased to 15 C. What is its final temperature? So again, I start with P1 V1 over T1 equals P2 V2 over T2. And now the question is, what is its final volume? So we're solving for V2. It doesn't look like anything's kept constant here, so let me do a little rearranging. If I want V2 by itself, I got to times both sides by T2. Cancels out over there, and I got to divide each side by P2 to cancel it out over here. So I get this equation, V2 equals T2 P1 V1 over P2 T1. All right, so now I can deal with these ugly numbers. Well, what is my new temperature? It's 15 Celsius, right? I go from 25 Celsius to 15 Celsius, but I need to convert that to Kelvin. So I end up with 288. I get 288 Kelvin times my initial pressure, which it told me it was 1 atmosphere, times my initial volume of 2.5 liters, divided by my new pressure, which they told me is 0.85 atmospheres, and my original temperature was, well, let's see, 25C would give me 298 Kelvin. Now let me check my units, make sure I got this set up right. Kelvin cancels out Kelvin, atmospheres cancels out atmospheres. I'm left with liters, which is my volume, so that's great. When I plug and chug, I get 2.8 liters as my final answer. There you go. Number 5, a sample of a gas originally at 29 Celsius and 1.25 atmospheres of pressure in a 3-liter container is allowed to contract until the volume is 2.2 liters at a temperature of 11 Celsius. What is the final pressure of the gas in atmospheres? So again, start with your P1 V1 over T1 has to equal P2 V2 over T2. And it looks like everything changes, nothing cancels out. So what are they asking me for? The final pressure. So I'm trying to get P2 by itself, which means I got to multiply T2 to both sides to cancel that out and divide by V2 on both sides to cancel that out. So now I have my equation. P2 equals T2 P1 V1 over V2 T1. So now I just plug and chug. My new temperature is 11 Celsius, which is 284 Kelvin times my initial pressure, 1.25 atmospheres, times my initial volume, 3 liters, divided by my new volume, which is 2.2 liters, and my original temperature of 29 Celsius, which would come out to be 302 Kelvin. Now let me check my units. Let's see, Kelvin cancels out, liters cancel out, I'm left with atmospheres. Beautiful. So now I can pick up my handy dandy calculator and beep bop, boop, and get 1.6 atmospheres as my final answer. There you go. Number 6, last one in the set. If the pressure and temperature is kept constant, how many milliliters of ammonia will be produced by the reaction of 50 milliliters of N2 gas with 150 milliliters of H2 gas based on the equation? So we can see from the equation that for every 1 N2, it'll react with 3 H2 to give me 2 NH3. Now when we're dealing with volumes of gases, it doesn't matter what the gas is, whether it be N2 or H2. If it's at the same conditions, it'll occupy the same amount of space for each mole of gas. If I have 1 mole of N2 and 1 mole of H2, they're going to take up the same volume at the same temperature and pressure. So we know, hey, we have 50 milliliters of N2 reacting with 150 milliliters of H2, giving us how many milliliters of NH3? Well, quite frankly, if you reacted all of these together, we're following the coefficient ratio, saying for every 1 milliliter or 1 mole of N2, I can react it with 3 milliliters or 3 moles of H2, which will give me 2 moles or 2 milliliters of NH3. So, 1 to 3 to 2, we got 50, we got 150. You could just pick any of them. So for N2 to NH3 ratio, it's a 1 to 2. So if I completely reacted 50 milliliters of N2, how much NH3 would I get? You'll get 100. And that's probably the easiest way to do that, especially since they don't tell you the temperature or the pressure. You can't use any of that. Just go, hey, I know if it's at the same conditions, the volumes are proportionate to the moles. All right, cool. I hope you found that helpful. See you in class. Okay, bye.